All right, guys. How you guys doing?
Good.
So, go ahead and introduce yourselves.
More.
All right, go ahead.
Brett Miller. I'm Andrew Bradbury.
Mustafa Hussain.
Alex Farrell.
All right, guys. So, what do we got here?
It's a game.
So it's a physically interactive game. We can move the monitor and the ball on the screen responds to said movements, much like it would in the physical world. And so the goal is to get to the target and avoid the holes. So you're the Hoverdisk and you try to,
Kind of has a little bit of a Tron theme in there.
Right, we have like sort of this metaphysical universe that we're simulating.
Oh, so that's one loss if it hits the red.
Exactly, and that's the only way you can lose is if you hit the red.
That's right, and you have to go through the maze to get to this point.
To get to the green target at the end.
That's right.
Exactly,
Well, there's
and that's
another
how
way
you
you
win.
can lose. Yeah.
Okay, so start explaining the process and everything else, and get into the image.
All right.
So the process, the computer stuff behind it. Okay, so
Well, the system is made up of several actual layers. There's the layer responsible for drawing everything onto the screen. That's the separate hardware module that has pretty much existed as standalone since about halfway through the semester as functional and has not been changed. That just reads data from block RAM and displays it on the screen. Nice and simple in concept. Then we've also got the CPU itself. That was finished a lot more recently, and that's mostly the same basic CPU everybody else has built in this class.
Based on the CR60 processor.
Although we have a few opcodes that make our things a lot easier. We then have a rather complete peripheral set. We've got GPIO control, we've got UARTs, we've got a SPI module, and then the various interfaces into the VGA controller itself. So this well-designed and complete peripheral set has meant that we've actually been able to implement some features that make our life a lot easier when developing software.
That's right.
So for the actual game motion, we're using a digital accelerometer, 3-axis accelerometer, which is communicating over SPI, so serial peripheral interface. We read in the raw values. We do a lot of scaling on them to get them to a proper realistic feel. And basically the ball builds up with velocity the more it's tilted. For example, if you have the ball moving one direction, you want to stop it, you have to apply an opposite tilt or an opposite acceleration in order to bring it to a stop.
which makes it feel very natural. And there's also this, it bounces off of walls really nicely, and it doesn't ever lose momentum, so that's nice. And it sort of acts as if it's a perpetual motion sort of world.
It acts as if there's no friction in the world. And so you can just hit walls and bounce around forever, technically, until you hit a hole and die. The collision detection took quite a while to get working.
And it is actually the most complicated part of this.
It ended up being about 13,000 lines of assembly. So it took,
That's quite a number.
Yes, it was quite a lot of instructions. We get you win on the screen when you win.
That's right.
But, yeah, it took quite a while for us to get that figured out and work out all the bugs. And so
That's right.
Mustafa, he designed it first in Python, which is over on that screen.
That's right.
Which is also very playable, and we did that so we could test the collision detection and make sure that was working, so we didn't have to debug problems in our logic with the collision detection while trying to debug assembly. So then we translate this code over to our pseudo C assembly language, and got it working on there.
It ended up being maybe 2,000 lines of our pseudo assembly language, and then that assembled to 13,000 lines of actual assembly.
Yeah, and you just say that again. 13,000 lines.
13,000 lines.
That's quite a number of assembly lines.
It's quite large.
That's right. That's
Debugging
right.
it was a pain.
That's right. Any last things you guys want to say?
At this point, we had proven the assembler was functional.
That's right. That's right.
So if you'd like to hear about our explorations that we did on the side, there's a couple things that didn't make it into the final project. One of them is a genetic algorithm that creates maps, and the fitness function for the genetic algorithm assumes that the longer the path is from the start to the finish of the map, the more fit it is. And it ends up with maps that aren't very playable, but they're really long. Like they're over here if you want to see it. We'll pick it up on the camcorder.
We're out of time.
Out of time? Okay, that's the genetic algorithm map. And we also simulated refraction in software, so we could have like a glass ball if we came to that.
Guys, very well done. Thank you very much, and hope to get lots more nice and awesome projects from you guys. Thank you very much.
Thank you.
Thanks.